Hi, welcome to this video. In today's video, I'm going to do a very interesting problem of International Mathematical Olympiad of 2019, the question number 4, okay? So the question will find all the couple k, n are the integer number, okay? Satisfied this equation, okay? K factorial equal to the product of 2 to the n minus 1 multiplied by 2 to the n minus 2 and so on all the way down to the n minus 2 to the n minus 1, okay? This equation is considered, if on the left hand side is a k factorial, on the right hand side is a product. There is a relationship between the k factorial and even number 2 to the n, okay? So we are going to show after certain points there is no solution for this equation, okay? So that's the purpose of this problem, okay? Let's start now. Write this one, k factorial equal to the n minus 1 multiplied by 2 to the n minus 2 multiplied by 2 to the n minus 2 square all the way down to the n minus 2 to the n minus 1, okay? I'm going to pull out number 2 from the second term, number 2 to square from the third term, number 2 to third from the fourth term, and 2 to the n minus 1 from the last term, okay? As a multiplier, okay? So it's giving me 2 to the 1, 2 to the 2, 2 to the 3, and so on all the way down to the n minus 1, okay? Factor 2 to the n minus 1 minus 1, okay? So this one is giving me 2 to the 1 plus 2. This one gives me 2 to 1 plus 2 plus 3 and so on all the way down to 2 to the n minus 1, okay? Factor the product of p to the k goes from 1 to the n. So I don't care about this term, I'm just putting this like this. It could be anything, okay? I will have nice arithmetic, okay, expression. So this one, so n minus 1 over 2, product of p to the k goes from 1 to the n, okay? Now what I'm going to do now, I'm going to write k factorial equal to 1 multiplied by 2 multiplied by 3 multiplied by 4 and so on. I'm going to use the Legendre theorem, okay? What I'm trying to do now, I'm going to extract the number of 2 from this factorial, okay? So, in the other word, how many number 2 that I have here, how many number 4 that I have here, how many number 8 that I have here, how many number of 16 that I have here. So the multiple of 2, so that's my goal. Why? Because I'm going to transfer this form into this form on the right hand side. So the left hand side expression should be the same expression as the right hand side, okay? As you see here, we have the right hand side, this is left hand side, okay? So the right hand side has to be written in the same form in order to solve this problem, this equation, okay? So what I'm going to do now, I'm going to apply the Legendre theorem by extracting the multiple of these numbers, 2, 4, 8, and so on, okay? So this one equal to k over 2, 3, the multiple of 8, that's mean 2 to the 3, and so on, okay? I'm not putting out all these numbers because the k factorial, it has too many numbers, okay? I'm picking up just what I need, okay? I'm just extracting the term that I need. So I leave the rest. As you see here, this one is multiplied by another product. We don't know this product, and also we don't know this product above because we don't care about it. So what I need here, I need the term that I need. Something written on this form, 2 to the exponent. This equation has solution unless you have this number, this term on the right hand side equal to the number on the left hand side. Okay, so this equation satisfy this condition unless you have this. So that's mean 2. This is equivalent to the n minus 1 over 2 equal to this one. So this one I can express it as 2 to the sum of floor of k, 2 to the k, 2 to the n, and goes from 1 to infinity. Okay, so the same thing here. This is sum floor of k, 2 to the n, and goes from 1 to infinity. So equivalent n minus 1 over 2. I'm taking this one out of exponent, so I will have sum floor of k over 2 to the n, and goes from 1 to infinity. So what do you know about the floor? Floor is always inferior than number because we have fraction, strictly inferior than k, the sum k over 2 to the n, and goes from 1 to infinity. Okay, this is nice classic geometry series. Okay, you will have k, as you see here, the sum of 1 to the n goes from 1 to the n and goes from 1 to infinity. Let's put the first term 1 over 1 minus 1 over 2. Okay, we will have number 1 here. Okay, this is geometry series 1 over 2, 1 over 4, 1 over 8, and so on until you get the last term 1 and the ends to the 1. Okay, I have this. Now I have inequality. I have transferred equation to the inequality. Okay, so now n minus 1 over 2 inferior or equal to the k. Okay, f to the n equal to n minus 1 over 2 factorial, strictly inferior than key factorial. What is the key factorial? It's the same that you have above. Okay, now we get arrived here with this expression. Okay, now our solution of this, now the solution of this equation is satisfied this inequality. Okay, so the solution of this, in the other word, the solution of this equation is located in this expression. Okay, but I'm going to show the solution of this equation is not satisfied this inequality for all integer numbers. Okay, what I'm going to do now in this step, I'm going to show this expression is not true for all n superior or equal to the 6. Okay, in the other word, this equation doesn't have solution if n is bigger or equal to the 6. Okay, I'm going to show that. But before I use induction theorem, I'm going to check the basic points where I can start my induction. Okay, let's climb. So we climb n minus 1 over 2 superior or equal to the k equal to the n minus 1 to the n minus 2 to the n minus 2 to the n minus 1. Okay, for n bigger or equal to the 6. Okay, see here, this is smaller than 2 to the n, smaller 2 to the n, this number smaller 2 to the n. Okay, so in the other word, so this one, I will leave this is minus 1, 2 to the n minus 2, and so on to the n minus 1. Okay, if you take a look at here, you have this number 2 to the n squared equal 2 to the n multiplied by 2 to the n, 2 to the n, and all the way down. Okay, So if you take a look at here, 2 to the n is bigger than this one. The n is bigger than 2 to the n minus 1. So 2 to the n is bigger than 2 to the n minus 2, and so on until you get the last term. 2 to the n is bigger to the 2 to the n minus 2 to the n minus 1. Okay? If I proved this one n minus 1 over 2 is bigger than 2 to the n square, is enough, equal to 6. 6 minus 1 over 2 factorial. Okay? Equal to 15 factorial. 15 multiplied by 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay? So if you calculate these terms from 11 to 8, you find 2 to the 12. Okay? If you calculate 7 to the 4th, you will have 2 to the 8. If you calculate 6, I can rewrite on this one to the 4th. Okay? I'm picking up just these numbers. Okay? From here to here, I can pick up 2 to the 14. If you add them together, the whole thing, this one is giving you 2 to the 14 plus 12 plus 8 plus 4 is giving you 2 to the 36. 2 to the 36, that's mean 2 to the 6, 2 to the 6 square. Okay? That's mean this number is bigger. This number is bigger than 2 to the 6. Okay? So f of 6 is bigger. So that's mean f of 6 is bigger. To 2 to 6 2. Okay? You see number 6 is verified here. You see it is verified, this inequality. So I'm going to claim this true. Okay? Claim by induction, math induction. F of n equal to n minus 1 factorial is true, superior k factorial. Okay? Which is this one. 2 to the n minus 1, 2 to the n minus 2, and all the way down 2 to the n minus 2 to the n minus 1. Okay? I'm bringing this one at the top and continue with our problem. Okay? I'm going to calculate f of n plus 1 for n plus 1 to check if this hypothesis theorem is true. Okay? F of n plus 1 equal to the n square plus n factorial square plus n over 2. Okay? Multiply by n square plus n over 2 minus 1 this one is n square. If you calculate this one, so if you distribute this one, if you simplify this one, you will have n square plus n over 2 minus n factorial equal to the n minus 1. Okay? To the 2 factorial. This is f of n. Okay? So f of n. We already proved f of n as a claim, induction claim. We have this one is bigger, f of n is bigger than 2 to the n squared. Okay? So now each of these terms is bigger than 8. Okay? 8. Bigger than 8, and so on is bigger than 8. Okay? It's easy to check it. Okay, this one is all of them is bigger than 8 to the n equal to 2 to the 3n, which is bigger than 2 to the 3n. Okay? Also, this 2 3n is bigger than 2 to the n plus 1. Okay? So that's mean f of n plus 1, which is n square, which is n plus 1 over 2 factorial is bigger than 2. Don't forget this term, 2 to the n square multiplied by the 2 to the n plus 1 equal 2 to the n square plus 2n plus 1, which is 2 to the n plus 1 quinary square. Okay? Now we verified this term. Now we verified our hypothesis. So our claim is true. Okay? So we verified our claim. So we verified our theorem. So the claim is true. So that's mean implies f of n, which is n minus 1 over 2 factorial is bigger than 2 to the n squared. Okay? And in the same time is bigger than this product, k factorial 2 to the n minus 1, 2 to the n minus 2, 2 to the n minus 2 square, and all the way down 2 to the n minus 2 to the n minus 1. Okay? Thus, a contradiction. We found the term n minus 1 over 2 factorial strictly inferior than k factorial. In the same time, we found same term n minus 1 over 2 factorial strictly superior than k factorial for all n superior or equal to the 6, which is contradiction. Okay? That means this equation doesn't have any solution if the n is bigger than or equal to the 6. Okay? So that means there is no solution. The solution of this equation is located in this interval n is strictly inferior than 6. Okay? Now I'm going to check term by term, from n equal to 1 to n to equal to 5, because 6 is not included. Okay? I'm going to check term by term. I have n equal to 1, f of 1 equal to the 2, 1 minus 1, okay, which is 1. So the family solution of this one for n equal to the 1, k equal to the 1, okay. So let's check n equal to 2, f of 2, have 2 to the 2 minus 1, product 2 to the 2 minus 1, okay, minus 2. So equal 2 to the 2, 2 to the 2 is 4, minus 1 is 3, multiplied by 4 minus 2 is 2, which is 3 factorial. So that's mean the solution of this one n equal to 2, k equal to 3. Okay. The solution of this f of 3 is located between f factorial and 6 factorial, which is not solution of this equation. Okay, because the solution of the equation has to be written on this form, like this: k factorial equal to the m factorial, for example, has to be the same on the same form. So f of 4, for n equal to the 4th, okay, we don't have the solution as well, because f of 4th equal to 20,916, okay, is located between 7 factorial and 8 factorial, which is not solution. So let's check. So f of 5 equal to 9,999,360, which is located between 10 factorial, which is located between 10 factorial and 11 factorial, which is not solution of this equation. So that only the solution that I have only 2 solutions. Okay, I have this one, I have the first one, 1, and I have 2, 3. Okay, so I have done with this problem. Thank you for watching. I will see you in next video. Bye.